Namaste everyone, welcome to Wave Optics class. So we have seen the fringe width, Young's double slit experiment and the interference of light waves, right? For different path reference, what is the type of wavefront that we have, or what is the type of final wavefront that we get, how is the superposition occurring in light and all. So we will recap all those things what we have studied and then we will move on. And this is Thomas Young. First of all, we have to get acquainted with who is Thomas Young. So this is the face, or this is the picture of Thomas Young, and very famous scientist. And he took two coherent sources. That means the sources which have constant phase difference and which have the same wavelength and almost equal amplitude. So that definition is important. Waves having constant path difference or constant phase difference, having equal amplitude and almost equal amplitude and equal wavelength. They are called coherent sources. And these sources are obtained from the same parent source. So he did that experiment by producing two coherent sources from the same original source and made these two sources to meet on a screen with the different path reference. And whenever the path reference was n lambda, the two waves produced bright fringe, and whenever the path reference is half lambda multiple, 1.5 lambda, 2.5 lambda, and so on, then he got dark fringes. So that pattern is called interference pattern. Now we will study a little bit about that interference pattern. So this is Thomas Young, and his experiment, and that is a double slit experiment, gave a very energy boost to the Huygens wave theory, because Thomas Young was able to explain the interference experiment only using wave theory. So wave theory could explain interference. That's why people started supporting wave theory. What Huygens said, the light is a wave, is true, and you can't explain interference experiment without taking it as a wave or taking it like a corpuscle, taking it as something else. It is not possible. It is not possible to explain interference. So if you want to explain interference, you must take light as a wave. So Thomas Young's experiment gave a very good support to Huygens wave theory. So he took a single source of light, and that is kept in front of a small slit, and the light from the first slit was made to fall on two separate slits, and these two slits made the light to pass through two holes, and finally they are made to interfere on the screen. And this distance should be very large compared to these two sources. You know for what reason? Because the light coming from this coherent source and this coherent source, they must fall on the screen with the small angle. They shouldn't come in opposite direction or at 90 degrees or so. They should fall on the screen at very small angle, so that crest meets the crest almost in the same direction. Okay, so the two sources are the two coherent sources. Of course, they are coherent. They should have the same amplitude because the slits are of same width, and they should have the same wavelength because they are coming from the same parent source. So they are made to interfere on the screen. So this D is capital D is the distance between the sources and the screen. Distance between the sources is called small d, and it is always as small as possible. So this is what the interference pattern that you see if you observe it in a microscope. So if the pattern is observed from here on a microscope, you will get it like this actually. You can't see, you can see here some dark lines, black lines, and white lines, right? In between white lines, you have black lines. But actually, if you look through a very high resolving microscope, you will find that intensity is not suddenly varying from black to white, black to white. It is slowly changing from black to white. So bright fringe slowly changes into dark. Dark slowly changes into bright. It is not a sudden change. So if you draw a graph of intensity versus distance, path difference versus distance, when the path difference is 1 lambda, you get a bright fringe. And when the path difference is 0 lambda, you get a bright fringe. When the path difference is half lambda, you get a dark fringe. Intensity falls to 0. Intensity rises to maximum. And you see, this is a smooth curve. It is not like a triangle. So if it was like a triangle, we could have, or if it was like a square like this, rectangle, the graph was like a rectangle, then we could have concluded that suddenly the intensity becomes 0. Like a barcode in a commodity. If you go to a shop, if you purchase anything, there are barcodes. Their intensity is suddenly rising to 0, dropping to 0, suddenly rising to maximum. So it is not gradual change, but this is a gradual change. because the two waves will interfere with different phases. Suddenly they are not coming to 180-degree out of phase and all of a sudden coming to 0-degree out of in phase. It is not so. Gradually 0-degree changing into the phase difference, changing into 30-degree, 60-degree, 90-degree, then 180, exactly opposite to each other. So such things will happen. So intensity keeps on changing. So the graph of intensity versus path reference is like this, and this intensity maximum corresponds to a central maximum, somewhere bright fringe, and next dark fringe, next bright, next dark, and so on. Okay, we will analyze it. In our day-to-day life, sir, can you give some examples where we see interference pattern? Definitely, I can give many examples. Soap bubble appears colored. That is because of interference. Sir, where are the two sources of light? Where do they meet each other? Why do they produce colored light? So all these answers you must think it of. Now, for the time being, I don't go into that. Here, the two sources are produced when the sunlight enters into this thin film. Some part of the light gets reflected, some part of the light gets refracted, and the difference in the distance traveled by the reflected wave and the refracted wave is equal to the thickness of the film, isn't it? Don't you think so? Imagine sunlight falling on this thin film, this thin soap bubble. The light which is reflected from the outer surface of the soap bubble will travel like this, and the light which is going inside and getting refracted and reflected, it will be having some path difference, because the extra distance traveled by the light which is going in is equal to the thickness of the thin sheet. So whenever there is a thin film, we get colors. That is not because of dispersion, that is because of interference, and different colors meet at different positions, and they give colored appearance. So thin film of soap and thin film of oil on the surface of water. Whenever there is initial raining, oil on the road just starts floating on the water when it is raining, in the beginning only. And that oil layer is a very thin layer, it appears colored, and because of multiple reflections and refractions, you get different sources of light. Some layers of some rays of light enter into this oil layer and they come out, and some rays of light will be reflected from the top layer of the oil itself. So they have a path difference which is equal to thickness of the thin film. So they produce and they interfere on your eyes and produce colored appearance like this. Now in cameras, in order to protect the lenses, a thin coating film is given on the camera lenses. So that thin coating reflects and refracts light, and those two lights will interfere and they produce colored fringes. So this color, the thin film coating given on the camera lenses, and soap bubble appearing colored, and oil on the surface of water appearing colored, all these are because of interference of different lights which are reflected and refracted. Okay, so remember this, what are the consequences of your interference, or wherever you see interference in your day-to-day life. There is one more property of light, that is called diffraction. So in diffraction, remember, you have these examples. CD appears colored. One side of CD, the writing part of the CD appears colored. When you hold a razor blade against a light, the edge of the razor blade is not very sharp, it is blurred. Spider web appears colored against sunlight. These are all because of diffraction. What is diffraction? Why does it appear colored? We will see it in the next chapter. But just to have a difference, I have shown. So these are all thin films appearing colored. That is interference. And this diffraction, here you have the examples. Now Thomas Young took a single slit, and light is made to pass through that, and light from the single slit is made to pass through two slits, and he used Huygens wave theory to explain interference. So he took it as wave fronts, the two wave fronts coming from S1 as well as S2, as they pass through here between the gap of screen and these slits, when they pass through, at some places crest falls on trough, that produces minimum. At some places crest falls on crest, that produces maximum. So you get maximum light. So we are talking about light now, not sound. So maximum light, minimum light, maximum light, minimum light. So you get a continuous variation of maximum and minimum light. But remember, this maximum light suddenly doesn't change into minimum. Gradually it becomes dark, then gradually it becomes bright. Of course, that pattern cannot be seen here. If you want to see that, you should have a very good microscope which will show each and every variation. Here it looks as if the bright red light suddenly changes into black. Again bright red, again black, but it doesn't happen so. Our eye is not able to discriminate all these things. But actually in practice, the central maximum will be the brightest. As you move away, the brightness goes on decreasing. This is the point where the first dark fringe occurs, because light traveling from here to here, light traveling from here to here have a path difference of half lambda, whereas light traveling from here to here and here to here, they have a path difference of 0 lambda. Here 1 lambda, 1.5 lambda, 2 lambda. So they have a distance difference. You just remember that PPT slide where the two persons walking, when they walk here, they have equal footsteps. When they walk here, here they have 1.5 footstep difference. So their footsteps don't match. Here they have a footstep difference of 1 lambda, but that doesn't matter. Their footsteps match. So wherever there is a half difference of path, there is a crest falling on trough, and that produces destructive pattern that you know it. So this is just an animation which shows a parallel beam of light is incident on two slits, and we get spherical wavefronts here. And as the two wavefronts superpose, at some places you have permanent dark. This is the place where crest of one falls on the trough of another, and this is the place where crest of one wave falls on the crest of another. You get bright fringe. So you can see here bright, dark. Can you see here bright place where crest and crest fall? Bright, dark, bright, dark, bright. That is called interference pattern. So this is another setup, simply a diagram. So here you have a source of light. It is made to pass through two slits, and then you get interference pattern. So the central bright fringe and all. Of course, this is not exactly interference, just I have shown it. Okay, this is how you can get the photograph of interference pattern. The two sources, they pass, and when they start interfering, they will produce bright, dark, bright, dark, bright, dark fringes like this. Okay, now we will move on to the actual analysis of it. Now suppose if you have a wave, whether it's a light wave, whether it is a sound wave, water ripple, whatever be the wave, any wave is characterized by many things like its frequency, how many number of oscillations does it make in 1 second, and its amplitude, what is the maximum displacement in positive or negative direction, rho, density of the medium in which it is traveling, that will also decide its intensity, strength, field, energy, etc. And v is the speed with which it is traveling. Now, if you consider all these things, we are interested with I is directly proportional to a square. That is what we are interested with, because whenever two waves superpose, the new wave formed will have same frequency, and the new wave formed will be in the same medium. New wave formed will have the same velocity. So when the two waves superpose, there is no change in velocity, density, and frequency, etc. There is a change in amplitude only. When the waves superpose constructively, amplitude grows up. When the waves interfere destructively, waves cancel. So that's what we observe. So we are interested with intensity of any wave, whether it is a third wave produced because of the superposition of two waves, whether they are individual waves, whatever it is. Intensity is directly proportional to square of the amplitude. Okay, if you move on. Now there are two waves here. One is red, another is almost black. They are starting from the same point and ending at the same point. No path difference, no phase difference, and path difference is 0, phase difference is 0. They are moving together identically. If the amplitude of both the waves are equal, what is the resultant wave here? Do you see this red wave or black wave? We neither see red wave, we nor see black wave. We see a different wave which is highest in amplitude, A plus A. So resultant amplitude is A. Here, now you have to remember a new formula. Of course, it is not a new formula for you. It was a known formula to you, but that known formula is used in some other chapter like vectors and forces. You have to bring it here. Sir, if two waves superpose like this, and if the phase difference is 0, what do you mean by phase difference 0? The crest is occurring at the same place, trough is also occurring at the same place. Crest at the same place, trough at the same place. If it is so, what is the amplitude of the resultant wave, sir? If the amplitude of this is A, another amplitude is B, what is the resultant wave? Here we know that it is A plus B. But do you have a general formula to find out A plus B? Very similar to the formula of forces. When you have two forces, 4 Newton and 3 Newton, acting at the same point in different angles, what is the resultant formula? R is equal to root of A square plus B square plus 2AB cos theta. Very simple. Where is theta there? It is the angle between the two forces. And the two vectors or the two forces may have any angle. When they are in the same direction, we write it as A plus B. When they are in the opposite direction, we write it as a minus b, because that formula r equal to root of a square plus b square plus 2ab cos theta, when different values of theta are given, cos theta will be different and the answer will be different. In the same way, here today, we will apply the same formula to obtain the resultant of the superposed two waves. Sir, what is the phase difference now? It is 0. So what is the resultant wave? Because they are superposing with crest and crest, resultant wave should be highest in amplitude because they are together now. So use this formula. Of course, I didn't use A and B. I used two waves of equal amplitude because we want coherent sources. A square plus, what is A? Here A, that is B. B is also A. A square plus 2AB cos phi. This is the formula I am going to use. Resultant amplitude of the resultant wave, when two waves of amplitude A and B superpose on each other, when their phase difference is phi. Root of A square plus B square plus 2AB cos phi. Okay, I have taken B also as A because they are identical waves, coherent waves. COHERENT, coherent waves. R is equal to root of a square plus 2AA cos 0, because there is no path difference, there is no phase difference. Initial superposition. So what is the answer for this? Do you get A plus B or A plus A? Yes. A square plus 2A square. Cos 0 is 1. 2A square. Totally 4A square. What is the root of 4A square? 2A. Is it so? So this formula is a very good formula to find out the resultant of amplitude of two waves when they produce their resultant wave when they superpose. Okay, this is one condition. Sir, this type of superposition is occurring in which condition? In Thomas Young's double slit experiment. Very simple. You have two sources of light, S1 and S2. And remember, all these things you have to understand. That's all. Nothing question will be asked from this. Of course, except 1 or 2 more questions. This is very much needed. This explanation is very much needed while you solve the problems. Today, I have taken up some 3 to 4 problems which were exactly repeated many a times in the final exam. Every time a question, either derivation of beta, that is fringe width, or a problem. It's 100% for the theory exam. And one or two problems for NEET exam and CET exam quite common. So under this one only. So you must know each and every corner of this experiment. Okay, the two sources S1 and S2 separated by a very small distance, and the screen is kept at a very far distance. When the waves from here reach here, waves from here reach here, the distance is same, no path difference. And how do they meet? Crest falling on crest, no phase difference, phi is 0. This is the place where exactly the amplitudes add up. This 2A occurs because phase difference is 0. Both travel equally. Of course, this is the place where amplitude is 2A. If the amplitude of the first wave is A, second wave is A, here the amplitude is 2A. What about intensity? Intensity of the first wave is A square. Intensity of the second wave is proportional to A square, not equal to A square, because there are other factors also. If the intensity of the first wave is proportional to A square, intensity of the second wave is proportional to A square. After superposition, whether the intensity of the resultant wave is 2A square, no, it is 4A square. Very, very strange, you see. Amplitude of this wave is A. Amplitude of this wave is A. So what is the intensity of this wave? Proportional to A square. What is the intensity of this wave? Proportional to A square. When they superpose, it is not 2A square, it is 4A square. Why? Intensity of the resultant wave is 2A. Sorry, amplitude of the resultant wave is 2A. What is its intensity? It should be proportional to 2A whole square. What is 2A whole square? It is 4A square. What is 4A square? 4 times this intensity. Because 1A square is proportional to I naught. What about 4A square proportional to 4 I naught? So intensity of the central bright fringe is 4 times the intensity of these individual sources. Just think of the situation. You have a bright bulb, you have a bright bulb. When the waves from each bright bulb come and meet here, what is the brightness here? Brightness of the light here. It is 4 times the brightness of either this one or this one. It is not 2 times. So intensity of the central maxima, central bright fringe. So whatever we have seen here, we have seen that diagram here. Yes, intensity of the center, any bright fringe for that matter, because any bright fringe is a place where amplitudes add up. So this bright fringe or this bright fringe is 4 times brighter than the individual sources. from this source, the brightness of the any bright fringe is 4 times greater and amplitude is 2 times greater. Why intensity is 4 times greater? Simple reason, intensity is directly proportional to square of the amplitude. That's all. So what about the other factors, sir? 2 pi squared, f squared, rho v, don't they change? No, they don't change because every wave is traveling in the same medium. So no question of these two factors changing. Frequency and medium, velocity, that doesn't change, only amplitude changes. So remember, if the intensity of the two interfering beams is I naught, the intensity of the central maximum is 4 I naught, not 2 I naught. If the amplitude of the two interfering beams is A, then the amplitude at the central, bright fringe is 2A. Amplitude is 2A, but intensity is 4 I naught. What is I naught? I naught is the intensity of each wave. Where here, what is here A? A is the amplitude of each wave. Okay. Now go to the dark one. First dark. What is the problem here? Why don't we have light at all here? The wave traveling from here has traveled certain distance, and this wave has traveled this distance. But unfortunately, when this wave reaches here, it may produce crest, and this wave, by the time it reaches here, it produces a trough. Crest and trough cancel each other. No vibration, no wave is seen here. Since these two are light waves, there is no light here. It is a dark place. So what is the amplitude? A minus A, 0. Why it is 0? Because the two waves are superposing with their opposite phase. The crest of one falls on the trough of another. Suppose this is water ripple. What about the molecule here? The molecule of water. If one wave travels like this, at the same time, simultaneously in the same medium, another wave travels like this. What is the condition of this molecule? This molecule says, sir, this black wave is black ripple is saying, asking me to come above, and red ripple is asking me to come below. What should I do? I am sitting quietly and I don't vibrate at all. So no wave is produced. A minus A. Do we get A minus A in that formula? Yes. Apply the formula once again. Resultant amplitude is equal to root of A square plus B square plus 2AB cos 180. Okay. Here I have used both A's. A square plus 2AA. Cos 180 is minus 1. This is 2A square. This is 2A square. 2A square minus 2A square, because you have a minus 1 here. What is the answer? Resultant is 0. No resultant wave at all. So that is the place here. Okay, I can move forward. This is the place. A wave traveling from here, the crest has fallen on the trough of this. This is the place where we get dark fringe. Amplitude is 0, intensity is 0. So see, if the amplitude of each wave is A, and if they superpose at a place where the crest falls on trough because of the distance difference. Somebody was asking me, sir, what is the path difference? What is phase difference? Path difference is the distance difference. This travels certain lambda, say 6 lambda. This travels only 5.5 lambda. What is the result? The crest of one wave falls on the trough of another. You see, half lambda difference. This has traveled how much? This has traveled lambda extra than what this has traveled. So this lambda extra makes the crest falling on trough. Resultant wave is 0. No intensity here, no brightness here. Amplitude is 0, A minus A. If the intensity is directly proportional to amplitude, amplitude is also 0. Intensity is also 0. This is a dark fringe. Now, sir, here it is bright. Here it is dark. Whether this bright is suddenly changing into dark? No. Here you can see it very clearly, right? In this diagram. And in this diagram, intensity of brightness goes on decreasing, 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 and finally it becomes totally dark. As you go above, again the darkness decreases, becomes brighter, 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 and it becomes very much brighter here. So now if you look into this, sir, here it is very bright, here it is very dark. What about in between? It is neither bright nor dark. How did the two waves coming from here and here, they have overlapped here or superposed here? It is like this. You see, we have studied crest falling on crest. That is the first case. Crest falling on trough, second case. Now crest is not exactly falling on trough, or crest is not exactly falling on crest. You see, the crest of this wave is falling on the 0th position of this wave, not to the -1 or not to the crest of this one. This is another superposition. So waves may interfere anyway, right? For example, if you say, sir, a person walking here has given 4 footsteps. What about this one? 4 footsteps. What about here? Here, one person has taken 6 footsteps, and this one 5.5 footsteps. Okay, what about here? It may be some fraction, right? This person may be showing 5.8 footsteps, and this person may be showing some 4.9 footsteps. So there is some difference. So that produces neither bright or nor dark. We will go to that. So what is the phase difference between these two waves, sir? Now path difference is lambda by 4, this one. It is lambda by 4. And phase difference is pi by 2. When one wave is at 0, another wave is at highest, then it is called pi by 2 path difference. If the phase difference. If phase difference is pi by 2, that means the crest of one wave is exactly on the mean position of another one. Yeah, wherever you see. For example, here, the crest of this is at the 0th position. The crest of this is at the 0th position of the other wave. Crest of this red wave is at the 0th position of blue wave. So now if this is the condition, what happens is you have to put cos 90, root of a square plus 2a cos 90. Cos 90 is 0. So what is the answer? Root of a square plus a square. That is root 2 a outside, root 2a. This is the resultant. So now you see, what is the intensity here? Intensity is square of the amplitude, 2a square. So for entrance exams and for theory exams, problems, this is very important. You must understand, don't by heart all these things. So the place where the phase difference is 90, resultant amplitude is root 2a, and resultant intensity is 2a square. That means, come back to the diagram. Intensity of one wave is proportional to a square. Intensity of another wave is also proportional to a square. At the place where they superpose with crest on crest and trough, they interfere constructively. Brightness is 4I0, amplitude is 2a. At the place where the dark fringe is produced, here and here, intensity is 0, amplitude is 0. But here is a place where intensity is neither maximum nor minimum. It is not a brightest spot nor a darkest spot, because intensity gradually changes into darkness. So this is not perfectly dark, perfectly bright. What is the phase difference? It may be 90 degree, because you see the amplitude, root 2a. It is neither 0 nor 2a. It is root 2a. What is the intensity? 2I0. It is neither 0 nor 4I0. It is somewhere 2I0. Similarly, you can assume one more angle, 60 degree phase difference. This may be 60 degree phase difference. If it is 60 degree, root of a square plus 2aa cos 60. What is cos 60? Half. When you put half here, 2 gets cancelled. Half here, write it like this. And this 2 gets cancelled. A square plus a square plus a square. 3a square. Root 3 outside the square root a. And this is the place. And here intensity is proportional to square of the amplitude. Of course, I have tried proportional to, not equal to. Very sorry. Intensity is proportional to 3a square. Here, I might have written it, but I have written direct amplitude. Amplitude is a here. Amplitude is a. They superpose. So here it is neither dark nor bright. Somewhere here. Then this is the place. Of course, I have written it here. This is the place where intensity is 3I0 or root 3a. Root 3a whole square means 3a square. I0 is proportional to a square. Then 3a square is proportional to 3I0. This is 3I0. So intensity here is 4I0. Intensity, of course, here it should be 4I0 intensity. I have to correct this as 4I0. Okay, I'll do that. So intensity here is 4I0. Intensity here is 0. So in between you will have 1I0, 2I0, 3I0, and so on, right? So intensity gradually changes. Now I have a question. Sir, the first wave had intensity I0. Second wave had intensity I0. When you came on the screen, you got 4I0 on the brightest place. Whether conservation of energy has been violated here? Because you got more energy, 4I0. But sir, here there are some other places where there is no intensity at all. That is why interference is the redistribution of light energy. We didn't get extra light here. We used these two lights and made them to superpose here and got brightest light. We made the same light to come here and made them to superpose, and we lost all the light here. But average is I0. See, sorry, 2I0. Intensity of this is I0. Intensity of this is I0. So what is the total energy given out from these two slits? 2I0 in terms of total energy. So total energy coming out of this slit and this slit is 2I0. What is the total energy distributed? It is not only 4I0. At some places we don't have light at all, right? So how to prove it? You get the average. Average is 4I0. Here, sorry, 4I0 plus 0 divided by 2. Average I am taking. Average means two numbers added divided by number of numbers, 2. 4I0 plus 0 by 2. Is it not 2I0? That is the total energy here. Energy coming out of this and coming out of this. So law of conservation of energy cannot be true and cannot be false anywhere. It should be always true. If the law of conservation of energy is such a universal law, natural truth it is, then here also it should be true. If two waves of intensity I0 and I0 superpose on each other on the screen, then the brightest point will have intensity 4I0, which is 4 times greater than 4 times the intensity of the individual sources. That doesn't mean that we have produced extra energy. It is redistributed. That means at some places we have lost the light completely in order to sacrifice for the brightness of the brightest fringe. So they have donated all their intensity here. Here they have lost it. That means the average intensity is 4I0 by 2, 4I0 plus 0 by 2. That is 2I0, which is same as this one. So this is what you should know. This may be a 1 mark or 2 mark question. In what way they will ask, I don't know. So what is average intensity on the screen? It is 2I0. What is the maximum intensity on the screen? 4I0. What is the minimum intensity on the screen? 0. What is the maximum amplitude? 2A. Minimum amplitude? 0. When the waves superpose at 90 degrees, what is the phase difference? What is the path difference? What is the resultant intensity? All these questions, all these answers, right? Okay, then if you move on, yes. Now we will go to that fringe width. You know that distance between two successive bright fringes is beta. And yesterday we have derived this in the previous class, lambda capital D by small d. Capital D is the distance between the sources and the screen, and small d is the distance between the sources. So beta is equal to distance between two successive dark fringes or two successive bright fringes. Okay, we will move on. Now, you may be asked to find out the nth bright fringe, nth dark fringe, and so on. For example, this is the 0th bright fringe, central bright fringe, where the two waves don't have any path difference. Now, if you move on like this, bright, next bright, 1 beta, next bright, 2 beta, like this, right? Where is the 5th bright fringe? So I have miniaturized this one. Now you can see here, this is the these are the two sources of light, and light coming from these two sources are falling over here, and that are producing the bright fringe, central bright fringe. And the next bright fringe is here, next bright fringe is here, third one bright fringe is here. What about the dark fringes? The first dark fringe is here, next dark, next dark. Distance from dark to dark is beta. What about bright to bright? Beta. Bright to bright is beta. What about bright to dark? It is beta by 2. Am I right? Distance from bright fringe here to dark fringe. Bright fringe here to dark fringe here. It is beta by 2. Now my question is, if you are asked to write, suppose in the problem given, we are going to work out the problem. You will get it now. Suppose in the problem, if it is given, the distance between or the distance of 5th bright fringe, or third bright fringe, if it is given, distance from the central bright fringe to the third bright fringe is 1 centimeter, if it is given. Then how many betas is equal to that 1 centimeter? That is what I want to make it very clear. Distance from the central bright fringe to the third bright fringe, this bright fringe to the third bright fringe is 1 centimeter. What is beta? See, distance from first to 0th bright fringe to first, 1 beta, 2 beta, 3 beta. So 3 beta is 1 centimeter, beta is 1 by 3 centimeters. That's how you can do. What is the distance of the 7th bright fringe? 7 beta. What is the distance of the 8th bright fringe? 8 beta, because you take central bright fringe as 0. 0 to 1, 1 beta. 0 to 2, 2 beta. So distance of the nth bright fringe is n beta, where beta is equal to lambda capital D by small d. Correct? So this is very easy to remember. What about this one? Dark fringe. Here you should be careful. See, bright fringe. First dark, half beta. Next dark, 1.5 beta, because dark to dark is beta. Correct? So second bright fringe is at, second dark fringe, D2, D3, D4. Second dark fringe is at a distance of 1/2, 1.5 beta from the central bright. Because you don't have a central dark fringe, you have a central bright fringe, right? So from the central bright to first dark, half beta. See, first dark, half beta. Second dark, 1.5 beta. Third dark, 2.5 beta. 1 beta, 2 beta, 2.5 beta. See which bright fringe you are referring to. Eighth bright fringe, which dark fringe you are referring to? Sir, eighth dark fringe, 7.5 beta. Sir, fourth dark fringe, 1, 2 beta, 3 beta, half beta, 3.5 beta. Third dark fringe, 2.5 beta. That means always half less. See, 2.5, third dark, 3.5, fourth dark, half, first dark, 1.5, second dark. So every dark fringe is situated at a distance of n minus half beta, where n is you are referring to the nth dark fringe. Seventh dark fringe is at a distance of 6.5 beta from the central fringe. You just keep on guessing it like this. Half, then 1, 2, 3, right? 1, 2, 3. So sixth dark fringe is at 5.5 beta. 11th dark fringe is at 10.5 beta. Formula is n minus half beta. So that distance from the central bright fringe to the remaining fringes. For the bright fringes, n beta. For dark fringes, half less. Remember it so, half less. That's all. Okay, that is one question. Another question is, you are using two sources. Now, how is the formula for beta? Beta is equal to lambda d by d, isn't it? Now, my question is, suppose if I ask you a question. If I frame a question paper and ask you a question, on what factors fringe width depends? 3 more questions, say. It's a very great honor for to write an answer for such a question. On what factors fringe width depends? It depends on the wavelength of light used. Whatever the color of light you have used, wavelength. It depends on the distance between the sources and the screen. It depends on the distance between the sources. Okay, that may be one question. It depends on the wavelength of light used, which are interfering, and it depends on the distance from the sources to the screen. It depends on the distance between the sources. Okay, that's over. Now, how will the fringe width vary when the D and D are changed? When the distance from the sources to the screen is increased, capital D. When the distance from the sources to the screen is increased, numerator, beta increases. So as the distance from the sources to the screen is increased, fringe width increases. As the distance between the sources is increased, fringe width decreases, because as small d increases, suppose you keep them at far away, the angle at which they fall keeps on increasing. And as S1 and S2 are taken away and away, as small d is more and more, fringe width decreases. So that may be another question. Now, how can you increase the fringe width in an Young's double slit experiment? That may be one more question. How can you increase the fringe width? By increasing the distance between the sources and the screen. By decreasing the distance between the sources, you go on decreasing the small d. By decreasing the distance between the sources, by using a wavelength, a light of larger wavelength. What do you mean by using a light of larger wavelength? That is the beauty. Now, that is what I am interested with. Increase the wavelength of light, that increases beta. That means you switch on a light here. I will use one light, say blue light. Now you forget about this red fringes, you forget red or brown or whatever it is. I am not bothered about color. One is blue, another is red for me now for the timing. Switch on a source here, blue source. What blue light will do? Blue wave fronts will hit on the slit. From both the slits, blue wavelengths will scatter everywhere. Scatter in the sense they move everywhere. Now what happens is, as the blue light from here passes and travels a certain distance, and blue light from here travels the same distance and superpose, they must interfere constructively, because how much waves this has created, same number of waves here also. So the crest should fall on crest. This should be a bright blue line. But as you move away, the brightness goes on decreasing, and there will be a dark one here, again a bright one, again a dark one, so on like this. Now measure the distance between one bright and another bright. Distance between two successive bright fringes is called beta. This is the beta fringe width for blue color. Now switch off the blue color. Switch on another light with a red color or brown color. Which has more wavelength? Lambda is more for red, lambda is less for blue. Now switch on red color. And the same screen, but I have shown diagram backside. On the same screen, now you get bright red and then dark. Again, bright red and dark. How are they spaced? That is the question now. Whether you get the central bright fringe at the same place as blue bright fringe is produced and red bright fringes are always formed at the same place. Whether the next bright is formed at the same place for the red one also? No. Because for red one, D and D are same. Capital D and small d are same. But lambda is not the same. For red color or brown color, lambda is more. So its fringes should be far away and far away. That means central fringe is common for all, because even if red travels here and red travels from here, or blue travels from here, blue travels from here, crest should fall on crest. They should superpose constructively, and whether it is a blue wavelength or whatever be the wavelength, this is a bright fringe. Now, the next bright fringe of red is little bit away. You see here, this is dark, this is bright. The next bright of red is far away compared to blue. Why? Because once the crest falls on crest of red, next crest falls on crest for red at a far away distance. When the gap is more, distance difference is more, for not for such a small distance difference, because lambda of red is more than lambda of blue. Wavelength of red is more, wavelength of blue is less. So you get the next bright fringe far away. You see beta for red, beta for blue. So now my question is, here is a problem. You will get a problem where, can you get a place where the fringes of red and blue coinciding with each other? Now, is that possible? That is possible. That is possible at a point. What you have to do is, we will show it in the problem. We will see that. Now, suppose the first blue is formed here, next blue is formed here, say, and the next blue is formed here. So when you keep on increasing the blue colors, the first bright of blue, next bright of blue, next bright, the fourth bright of blue may coincide with the third bright of red, isn't it? That is possible. We will come to that problem. Later on, we will discuss about this. Only the thing now I am interested with this, this is, if the wavelength is more, then beta is more. If the capital D is, that means distance from the sources to the screen is increased, where beta increases. If the distance between the sources is decreased, then beta increases. So then we will move on to one problem, and tomorrow we will see few more problems. Okay. So for the time being analysis, of course, here we have covered only 1 or 2 more questions. So till now in wave optics, I have covered some Huygens theories, 2 mark and 1 mark, and some wave fronts, their diagrams, and Snell's law proof using Huygens wave theory, that is 3 marks, and what happens when plane wavefront is hit on a lens, a mirror, all 2 marks, and then fringe width, 5 marks, and problems. And all these analysis, 1 mark, 2 mark, chill-repel questions. Read the problem. We will solve this and stop it once. In Young's double slit experiment, the slits are separated by 0.28 millimeter, and the screen is placed at a distance of 1.4 meter away from the slits. The distance between the central bright fringe and the fifth dark fringe is measured to be 1.35 centimeter. Calculate the wavelength of light used. Also find the fringe width if the screen is moved 0.4 meter towards the slit. Okay, next part we will do at the end. Also find the fringe width if the screen is moved 0.4 meter towards the slit. That is different. What about this one? Here you see the given data. The distance between the central bright fringe and the fifth dark fringe. Remember, fifth dark fringe, where is it? Yeah. Yes, fifth dark fringe. Of course, we don't have fifth dark fringe. Suppose it is the fourth dark fringe. Dark, 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 dark. First dark, half. Then 1, 2, 3 and half. Every nth dark fringe, n minus half. And some people use this formula in a different way. What they do is, they will write n plus half beta. If you look into some books, you will find that, sir, they have used for the nth dark fringe, they have used the formula n plus half beta. But they will put n next number, previous number. For example, 7th fringe, they will put n equals 6. Instead of that, you follow this one. Only one method is enough. For the 7th fringe, 6.5 beta, because every dark fringe is half beta less distance. Okay, we'll move on to the problem now. Yes, what do we write here? Fringe width is beta is equal to lambda d by d. Now, how is beta given? Beta is given in terms of the distance of the how much fringe, dark fringe? Fifth dark fringe, that is 4.5 beta. 4.5 beta is 1.35 centimeters. 4.5 beta is 1.3 centimeter, 1.35 centimeters. What is beta? Beta is equal to lambda d by d. Okay. Beta is equal to 1.35 centimeter by 4.5, and that is equal to 0.3 into 10 to the power minus 2 meters. Okay, minus 2 meters here, right? 0.3 centimeter. That is beta. Now, what is their question? Their question is to find out what is the wavelength of light used. First question. Okay, how to find out the wavelength? Beta is so much, 4.5 beta is given, and beta is equal to this by this, 0.3 into 10 to the power minus 2 meters. Now, beta is equal to lambda d by d. You have everything except lambda. You can find out what is lambda. Yes, 0.3 into 10 to the power minus 2 is equal to lambda, don't know, d, that is given in the problem, 1.4, and small d, 0.28 millimeter. So if you rearrange this, see, 14 twos are, right? 14 twos are, 2 threes are 6, so 600 nanometer. Check this answer, okay? That is left to you. It's a very easy question because you can see 1.4, 0.2 times this one, right? 0.2 times, and 0.2, 0.3 times 0.06, and then we have minus 7. Yes, you get 600 nanometer. Okay, you calculate it later. Once lambda is obtained, there is one more question in the problem. What is that? Calculate the wavelength. Also find the fringe width if the screen is moved 0.4 meter closer. What is beta? If the screen is moved 0.4 meter closer, that means capital D has to be reduced to 1 meter, right? 0.4 meter closer means you are bringing this closer. That means you have to, from 1.4, you have to reduce 0.4, right? So new capital D is 1 meter. You can use the same wavelength 600 nanometer. So 1.4 minus 0.4, screen is moved towards the sources, 1 meter. And beta is equal to, again, lambda, same lambda, capital D is new 1 meter, by small d is same. You will get this one. That is a new fringe width, 0.214 millimeter. So this is one problem. And we will work out some more important types. This is also important, but there is no much trick involved here, except what is the distance of nth dark fringe. That's all. And you may be given nth bright fringe also. Sir, nth bright, say fifth bright fringe is situated at such a distance, then what is beta? Or you may be asked to find out beta, and what is the distance of the seventh bright fringe? 7 beta. Eighth dark fringe, 7.5 beta. So like this. So that technique you must know. Rest of the problems we will see tomorrow. And there we will have two or three problems again. And that makes the idea of interference more and more clear. And then, of course, once you get all these ideas, you can definitely go to the entrance exam problems also, no doubt. You can join with that. You can study them also, no problem, because such ideas will give you very a good idea to solve the problems also, entrance exam problems also. Till then, keep watching the videos, study. Again, I repeat the same words. So take care of your health. That is very important, because we don't know when the classes will start. Once it starts, you must be very healthy and very active and cheering. You must be ready to come to the college. Of course, you may be ready to come to the college now also, but still, you have to take care of your health. So don't waste the time. Use it, utilize it in a proper way, so that the coming days will be very easy days. Otherwise, it will be hectic. Hope you will do so. Thanks for watching. Thank you.